Let me just stop and ask, how many of you are going to be using the water analysis object in your daily work? Just show of hands is good enough.
I will.
Dean, okay, good. Faisal, that's you. Dino? Yes.
Yes.
Brett, how about you? Okay. Mariana, how about yourself? Okay, so I guess not. So a couple of you will.
Yes,
You will. Okay, good.
I
But
will
that's good
use it.
enough. I do want to make sure that if I'm showing this, there's something relevance to it. That way I know if I should spend more or less time on it. All right.
It's extremely important to me, Ajay. Yes.
Okay, good. All right, so what we're going to do today is learn the mechanics of the water analysis object. Water analysis is one of the most complex objects that we have in OLI Studio because there are many functions or there are many adjustments that you may want to make in a water analysis. Or several at least, maybe not many, several. And I want to go through at least some of those with you. But the most important thing is knowing how to set it up. So first thing I want to do is I want to shrink my grid, my navigator panel, by minimizing everything in that list. Marianne, I see your hand is raised still. Was that just to say yes, or is there a question there too?
No, it is a question.
Okay.
But not a question, but a comment. I will use the water analysis, but I will also have a gas phase. I will have both together.
Yeah.
So for me, it would be good to know that, but also understanding how that phase will interact with a gas phase.
Yeah. And when that type of calculation, again, depending upon what your application is, we'll probably have a separate water and a gas analysis, and then we'll mix them together in the mixer. Now, if you're doing upstream oil and gas production, then we'll probably use the ScaleChem tool for that. Okay. But we'll deal with the actual tool that you use later on. The approach is identical. Okay. You essentially create your individual analyses and then you mix them together. So, okay, but let's just go ahead and get started. Now, the first thing we have to do in order to start accessing the water analysis is be at the top level object. So I need to go back to the top level streams, and in there you'll see the third option down is called Add Water Analysis. Double click on that. Okay. Now, the water analysis essentially is the way that you convert lab data to process streams. The water analysis can accept hundreds of different cations and anions, but 95% of the time, you only need like a dozen or so, or maybe, less than 20 entries. So what the software has done, what we have done in our UI is we entered, or we pre-populate the water analysis grid with the most common cations and anions that are the ones that most customers come to us with. And what you'll notice about this composition is that these are the compositions of natural water. Okay, you see sodium, these are all the alkalis, sodium, potassium, calcium, blah, blah, blah. You have you have iron here, it's reduced iron, make note of that. And then chloride, sulfate, bicarbonate, bisulfide, and organic acids. And then you have neutrals, dissolved CO2, dissolved H2S, dissolved silica, dissolved boric acid. Then in the middle, there's something called the total ions. In some cases, again, a lot of the analyses are done using what's called an ICP, inductively coupled plasma spectroscopy, or in some cases, mass spectroscopy. Anyway, making the short story long, when you're on the left side of the periodic table, when you're looking at it, the sodium, calcium, magnesium, things like that, those elements, when you put them in ICP, those elements are generally found as their ions, okay, in water. But on the right side of the plot of the periodic table, where you have nitrogen, arsenic, phosphorus, sulfur, etc. And if they can be measured by the ICP, right, you get total phosphorus, total silica, total sulfur, etc. Problem is, they're not found in water as phosphorus or silicon or boron or sulfur S+6. They're found as what they call their oxyanions, as phosphate or borate or silicate. So we have to help the customer out by allowing them to enter the data that they get from the ICP, which is usually total phosphorus, but knowing full well that it actually exists as what we call the oxyanion, phosphate. So you'll see that there's a third section here, or a fourth section here, where you can enter the ICP results as total ions, and the software will convert it automatically to, where you can add it as the element, but the software will automatically convert it to their oxyanions. And the term oxyanion, that just means that there's an oxygen present, and then that the molecule that's created by it is an anion in nature. So phosphorus, when it forms a phosphate, is an anion. That's the term oxyanion. Okay? It's really nothing. It sounds like a 25-cent word, but it's very simple in terms of what we're trying to explain.
AJ, quick question. Okay, so in here, when we're doing this water analysis, is it basically a stream that is understood to be predominantly water with all these species dissolved in it, or also this will apply in case of entrainment, emulsion, or vapor phase, or other phases whereby you have water present in droplet system, or even up as little as 100 ppm or 2% weight percent? This will apply to those cases as well?
No, it can apply to some of them, because what we're going to do is the lab is going to have a sample, and the sample is going to be a 1 liter sample. It comes into the lab. They'll probably filter it or digest it first. So they may filter out solids. They may even filter out things like emulsions, or even do things like solvent extraction to remove, let's say, the organics and then test it. So depending upon the experiment that gets done, you're going to use different pieces of the software to capture that. So let's say, for example, that I've got all the above. I've got this water sample that's got emulsified oil in there, and it's got a vapor phase, and it's got precipitates, right? Depending upon how the lab separates that out or does the analysis, that's essentially how you have to enter it into the software. So if they use like a 20 micron filter, for example, half micron filter to remove the solids or the organics, and they flash off the vapor, all you have left is the water phase. That goes in here. On the other hand, if they measure the whole, they take that 1 liter sample, right, and they essentially test everything in it. Then you can put everything in here, right? How much hydrocarbon was measured, how much CO2 was in the how much CO2 is present, etc. But then you have to be careful, because it's all based upon the volume of the liquid water present. So you then need to change your units probably to something like ppm instead of concentration, because concentration is based upon a liter of water.
Okay, so it would work. It would work probably better for predominantly water streams, but it could work for other stream if we pay attention how we do it.
That's right.
And play with the unit.
Yeah, you're right. You can't work concentration units because it's no longer a concentration-based process. Actually, it could be, but it's really not. And it's more of a ppm thing. So and in something like that, my guess is even to do that in the lab is too difficult. They're going to separate out the phases, because they've got to send the gas to a GC to get that composition. So they'll flash it, figure out how much volume comes from every liter of water, right? They flash it, they know the quantity of methane, propane, etc. And really, what you do is you create a new stream. I create the gas component from that. I create the dissolved water species, and they may even say how much sediment or solids they have, and what the XRD is of that solid, and you can add that as a third stream too.
Okay.
So there's a lot of ways to skin the cat. Really depends upon how you're consuming the data from the lab.
Okay. Thank you.
You bet. Yeah. Okay. So what we're going to do here is, anyway, so I was explaining, what I'm explaining here is that we've got a water analysis object that has the standard cations and anions already populated. But if you needed to add more stuff, essentially you go into your cation section or your anion section and you just start typing away. Let's say, for example, that you have manganese, Mn+2. You can type Mn+2 and press enter, and it finds it. Okay. In some cases, you're going to find that it's not as easy to add something. Let's say, for example, that they measured formate in the water. Okay. Cases like that, what you generally want to do is use what we call the search function. You can use it one of two ways. You can either, like, for example, type in the first three letters, then press the down arrow, and you'll find here's formate right there, right? Or you can press the down arrow and then start typing in. Either way works. Okay. What you'll notice is that when you do that, you may in fact see duplicate entries, formate ion -1. As it turns out, they're identical in nature. It's just that we provide multiple synonyms so that it's easier to find things. Okay. And on average, there are about 6 ways of entering a species in the software. Okay, what I mean by that is, no, more than that, 9 ways. There are about 6,000 species in the software, and there are about 60,000 entries. So actually, it's more like 10 ways of entering things. So usually you don't have a problem typing stuff in, but sometimes you do. And then when you do, say, hey, Jay, I can't find this molecule. How do I do that? And when that happens, you go into the search, binoculars there, and you can either start typing in things here, right? Or you can go to the periodic table and just start selecting what it is that you have. Okay, and then you can search for it this way. Okay, there's my formate anion. And then you just add it to the stream. Okay, so there's always ways of adding stuff. You just have to figure out what the most comfortable way is for you to add it. Okay. Now, in the chapter 4 manual, we go through this, I want to say, kind of extensively. So even though I'm only glossing over it, in the manual, we talk about different ways of finding cations and anions. And the reason why I'm spending a few extra minutes on it is because, again, there are certain aspects of data entry that can be a little confusing, and finding the species you're looking for is one of those. Okay. Now that we're done with that and talking about all these big important things, we're going to do a very basic calculation. So what we're going to do now is we're going to create 2 water analyses. Now I'm going to actually split my screen here, so you're not beholden on me to enter your data. I'm going to put this screen over here. Normally, I'd have the training manual on the screen instead, but I figured it's just easy just to show you the original water example rather. What I want to do is first, on the left-hand side, again, is your work area or my work area. On the right-hand side is what we're going to enter. Okay. So first things first, I want you, in this new water analysis that you created, I'd like you to rename it 4.2A high calcium barium. Okay, that's just a water. It's got a high concentration of calcium and barium. Now what we're going to do is you're going to look on my right side here, and you're going to start typing in the stuff that you see here. So the total dissolved solids is 35,000. Okay. Measured pH is 6.3. We don't have an alkalinity measured, don't have a TI, total inorganic carbon measured, but we have a density of 1.025. Then you're going to scroll down and you're going to add your total dissolved silica of 25 milligrams per liter. We don't have any total ions to add. So you're going to go to the next section, which is the cation section. And you're going to start adding the concentrations. 10,000 milligrams per liter of sodium. 2,000, I'm sorry, it's 350. It's not in order, by the way. 350 of potassium. 2,000 calcium. 800 magnesium. 300 strontium. 150 barium. Then on the anion section, 21,000 chlorides. Now the next one is bromide, right? So we have to add bromide. So Br -1, press enter. 150 bromide. Sulfate is 0.5 and bicarbonate 26. So take a few minutes, add that stuff in there. If you haven't used this before, again, it takes a little bit of getting used to. Don't be surprised if you end up with some red X's on the grid. If you do get a red X, you just have to press the delete key to get rid of it. Okay? And you just have to retype it in again. And I'm going to, well, I'll leave it as is. Here, I'm going to have to wait because I know entering stuff takes a long time, especially when you're new to it. When you're done typing and everything, just raise your hand. That way I know that you're ready to go. But this is a case where I actually have to wait for everybody to be at the same spot. Thanks, Brett. Everyone to be at the same spot because there's a procedure here. Oh, great. Thanks. Faisal, Xingjiang, thanks. So it's Dino and Marina. Wait for you guys to catch up. Let's keep on saying Dino. I'm sorry, Dino. There was a colleague. We had a consultant. Thanks, Marina. Consultant colleague working for us named Dino, and it's just comfortable with saying that. Okay. Dino, just let me know when you let us know when you're ready, then I'll proceed.
Yeah, I'm sorry, I'm ready.
Okay, good. All right, fantastic. Good. So that's step number one. Now, again, a water analysis, I said before, is a complex approach, right? Because we're taking disparate data probably coming from multiple instruments, right? The pH comes from a pH probe. Density comes from a densitometer or maybe a hydrometer, right? Your dissolved silica, that may have come from I guess I can't remember what type of experiment it was now. I want to say molybdate, but I think that's wrong. A different one experiment. Your cations are coming from the ICP. Chloride probably from wet titration. The sulfate probably gravimetric. So you've got all these different waters, all these different all these different measurements coming from different parts of the laboratory, and we're bringing them together and recreating a representative fluid. So as a consequence of that complexity, we have to actually build in ways of combining material. And essentially what we do is the important part is combining materials gives us what you call recorded properties and charge balances. And again, let me just jump to the punchline here. We just don't enter a water analysis and then start doing surveys or single points with it. We have to first reconcile it. So the properties that are measured match with the properties that are calculated, or vice versa. Properties that get calculated match the measured properties. Now what we're going to do is we're going to do that, you use what's called a reconciliation calculation object. Right here, you can see, in the upper right of the section, right? This is where I mentioned is our calculation section. There's something called an add reconciliation. In fact, it's the only thing you can do in a water analysis. So click on that button to add a reconciliation. What that does is adds a calculation object underneath the water analysis. Okay. It still contains the same information as what we saw before. But now if you look in the upper right-hand side, you can see we've got four, I thought there was five, four different calculation options that are going to be used to reconcile calculated versus measured properties. In addition to that, we have to balance the charge, meaning that we enter these cations and anions, but there is no guarantee that the system is electrically neutral, because just by design, labs don't measure everything in the water. And even when they do measure things, they measure total ions, total amounts or elements. They don't measure speciation. So the system will always be charged imbalance, and that has to be reconciled. Now, OLI reconciles things automatically, but in order to see how it reconciles, click on the specs button. Okay. In the specs button, the first tab you're going to see is something called charge balance. The charge balance is set to something called dominant ion, which is generally the safe bet to go. This means that the most concentrated species, either chloride, in this case chloride or sodium, will be added to the system. You can see here at the bottom of the window, it says, okay, right now there's a charge imbalance of about 24 milliequivalents, meaning that I added too many ions of cation and not enough ions of anion. Right? So I need to add essentially 23 milliequivalents of anion to the system. And since chloride is my dominant ion, that is equivalent to adding 849 milligrams per liter of additional chloride. Now, and that action occurs because we've chosen dominant ion as the approach. If instead, for example, I had chosen sodium or chloride, well, in that case, it turns out to be the same thing because sodium and chloride are the dominant ion. If instead I chose something called makeup ion, then depending upon what I pick, if I pick chloride, there's the 848 again. If I had chosen sodium instead, then it'll remove 550 mg per liter of sodium. Regardless of what you choose, the software is going to first balance the charge so it can do the next part of the calculation. And then
I'm sorry, AJ. So when you say dominance in terms of milligram per liter and then in terms of charge, is the software seeking neutrality by balancing ions and cations in terms of volume, or is it seeking neutrality based on charge neutrality?
It's charge neutrality. So in this case, we call it equivalence of charge. You see the EQ there? Those are the equivalents of charge.
Okay.
All right. So that then, again, that is the basis of what we call the balancing charge. That's always step number one. Step number two then is to, again, reconcile or bring together, make sure that the calculated properties, things like pH or alkalinity or total inorganic carbon, match what was measured in the lab. It's not always the case that what you enter here will in fact produce a 6.3 pH or a given alkalinity. So what we do therefore is when we choose one of these buttons here, we're instructing the software to change the composition of the water such that the properties that are measured here are matched by the properties that are calculated. Now, in this case, to keep things simple, we're not going to do anything special. We're just going to do what's called a no reconcile, meaning that we're not going to try and keep the pH to be make the pH 6.3 or balance or get the alkalinity where it's supposed to go. Okay. So now all you're going to do here is just press the calculate button. The software will add the additional chlorides to the water, the 848 milligrams per liter, and then it's going to calculate the pH, the alkalinity, the TDS, and the density, but without trying to match them, without trying to match the measured values. So when it gets done, what you're going to see is, Again, the summary section is always good for this. There's the amount of chloride that had to be added. We already know that. This is the pH that gets calculated, 7.43 compared to 6.3. So you can see the difference there. Here's the density, 1.023 versus 1.025. And then if we want to look at the TDS, then we would go to the report to look at the calculated TDS. Okay. But at this point, we have what we call a water that now can be used in a process. What I mean by that is it can be either sent over to a process simulator to build a process. It can be used to study corrosion. It could be used in single point or survey calculations like we did earlier today and on Tuesday. As long as you see the green checkbox here on the reconcile object, this stream is now ready for additional processing or additional studying. Okay, we're going to make one more of these, and then we're going to take a break. So let's add, one more time, I'm going to split my screen. Now what we're going to do is we're going to add a new water analysis. And it's going to be called high carbonate sulfate water. So now what you're going to do, again, you're over here on the left side where it says reconcile. I don't have anything in my action panel because I'm at too low of a level. So I'm going to go up at least one level so I can see the water analysis. And I'm going to add a new water analysis. We're going to call that 4.2b, high carbonate sulfate. Again, it's the same grid as we saw before. It's got our measured properties, neutrals, cations, anions, and then elements. What we're going to do now is take the data from the right-hand side and add it here. So now I've got a TDS of 61,000, measured pH of 7.8, density of 1.042. Then the silica is 10, potassium 200, calcium 25, mag 15, strontium 10, barium 0.05. And then I'm just going to add it, and then you guys take your time to add it. Chloride 35,000, sulfate 2,000, and bicarbonate 950. And you're going to do the same procedure. You're going to enter your data, add a reconciliation, and then we're going to calculate the properties.
AJ, question while everybody's entering. If, let's say there is a species, an ionic species or irradical that I'm interested in, let's say an amine, for example, that is not in your database or library, is there the option to add that manually?
No, because that ion probably has to be linked to a molecule. Let's say there's an amine, and that we haven't created that amine yet. Let's say it's something like, I don't know, cyclohexylpentylamine or something like that, right? Make that up. In order to make any use of that anion, you need to know the acidity of that anion, the basicity of that amine to start with, which means you have to have the molecule in there, and then at what pH it turns into the anion. But more than that, you need to know how volatile it is. So if this is going to evaporate or go into the vapor phase, then you want to have that property as well. So just adding the anion isn't sufficient if you want to actually do what OLI does best and give you the right set of properties.
Okay. Okay.
Yeah, we'll have to talk about that further. I mean, we have about 25 amines in the database right now. So we'll have to find out what you're missing.
Yeah.
And Faisal, your hand is raised. Was that from before to say you were done, or do you have a question?
Oh, sorry. Yeah, it was from before.
Okay, cool. Good. All right. As long as everyone's entered that data, then add a reconciliation object. Okay, again, so you click on that button called Add Reconcile. You create this object here. And once again, we're not going to go through all these these calculations here. We're going to just avoid that in this particular example. And we're just going to press the calculate button. Okay. And what I want to show you is, again, what happens. Again, there's just one thing we're going to do here that's going to be different. Okay, good. Now, the first thing you're going to look at once it's done is how it reconciled, right? And you're going to notice that the software says, well, in this case, the dominant ion was potassium because there was no sodium measured. Okay, so here's an example where you can say, well, is that actually accurate? Or was the sodium assumed based upon the chloride charge? Now, I did this purposely, or we did this example purposely to make the point that when you choose the dominant ion, again, it's going to take the highest concentration and add it. But in some cases, the lab comes back and it doesn't measure things because it assumes, or it assumes that if they measure chloride, that the counter ion is going to be sodium. So here's an example where you got an incomplete water analysis. The cation probably should have been sodium. And you can't just use the default settings. So what we're going to do together is we're just going to click on the specs button. And now this is where you change your dominant ion approach from dominant ion either to sodium or a sodium chloride or a makeup ion. And then you're going to select the sodium as the material to add. And now you can see it's going to add 23,811 milligrams per liter of sodium. So you press OK, and you press calculate again. Now it added sodium, 23,000. It produces a pH of 7.8, which is pretty darn close. The density is 1.040 compared to 1.042. And in cases like this, if you say, well, how do I know if it's sodium or potassium? Well, in this case, you can use things like TDS, right? The TDS here, we added 23,000 of sodium and we added it to 35,000 chloride. That's about 58,000. Plus everything else, it would produce about 61,000. If I had used potassium here, it would have added about 39,000 potassium. 39,000 plus the 35 would have automatically produced 74,000 TDS. So we would have known, oh yeah, that's way too much TDS because the TDS that was measured is about 61,000. So it's an example of where you're using multiple pieces of information to make decisions. Okay. All right. Okay, we're done now we're at a perfect stopping point for our break. So we're going to stop here. Let's take a 7-minute break. Come on back. And then what we're going to do is mix these two streams together. And that'll essentially get us through chapter 5. So let's take a break, 7 minutes. And when we get back, we'll do the next step. Yeah, Dino.
Really quickly, do you offer the services of providing thermodynamic properties for, let's say, different species or materials? Such, for example, if we have a not so known amine, and we need, let's say, vapor pressure, sublimation, boiling point, solubility, entrainment, all those properties. Is that something you do offer?
It is. Yeah. In fact, the way we added the 20 of the 25 amines was that way itself. We contracted a lab. It was done. Several companies asked us for similar amines. Actually, it was about a dozen companies. and we contracted a lab to measure the data. Then we developed from that the thermodynamics in order to do the modeling of it. And now that data is used from multiple applications, including gas sweetening, crude distillation unit, overhead neutralization are two common examples. Sour water stripping, and the entrainment in crudes, things like that. So a lot of refinery stuff on that.
Okay, so if I have a specific amine or some other species, I'll just send an email to Jim with that request.
No, it's
Or-
actually more of a business request. So what you do, you could go, I think, is it Mike? I don't know who the primary salesperson is. The good thing is they're all engineers, so they know what you're talking about. But then what they'll do is they'll have to set up a contract with Invista to essentially say what it's going to cost to do it.
Okay,
And you'll say
Got
either it's good, or you may say, you know what, let's see if anybody else is interested so we can share the costs, kind of thing. And then we'll
Sure.
have like a JIP. So
okay, good to know. Thank you.
you bet. Yeah. We're doing this right now. Actually, we've done a lot of these. And the one that's going on right now is actually not funded, not done. We're not the primary contractor, but there's an organization called, gosh, why can't I think of it? It's IFE. It's the Norwegian Institute of Technology, essentially, and they're developing experimental data for carbon capture, carbon CO2 transport, and the formation of acids because of impurities. And and that's a JIP consortium of about a dozen, let's say 10 companies. Then our responsibility is to create the thermodynamic properties so that they can use software to do the predictions instead of for the lab. And then there's another one at Southwest Research. That's where Sean used to work too, by the way. Southwest Research, where they're looking at high pressure H2S. And then we're going to extend thermodynamic properties to go into high pressure H2S. So, okay, all right, good. Okay, we're going to get started again. So what we're going to do now is we're taking these two waters. We really haven't spent any time studying the results of this, and we're really not going to, because it's really nothing special, really. But if you wanted to, you could always go to the report. And in the report, for any of these water analyses, you'll see tables that describe, what you entered, what was modified, okay, and then what the final properties are. So if I can just, maybe I'll spend 30 seconds describing it. The first table is going to be, again, what you've chosen. So we're doing a reconciliation. We're using, in this particular case, it's for the carbonate sulfate water. You chose what's called a user choice for the charge balance, because we couldn't use dominant ion, otherwise it was going to add potassium. You didn't choose any reconciliation of pH or alkalinity. You just chose the default setting. These were the starting conditions, or the test conditions, 25 C1 atmosphere. This is what was measured versus what is calculated. From a compositional standpoint, this is what you entered. The software made one modification to the water, okay, to reduce the water down to make 1 liter. Okay, and then from a charge balance standpoint, the software, it shows you what the charge balance inequality was, and then how much sodium was required to balance that charge. And then finally, just like we saw in the other day, the rest of the properties of the water. So here's the TDS estimate, 62,000 versus 61,000. There's the pH, the densities we'll see down here, etc. Okay, and then the rest of the speciation. Okay. So it's the same output for the most part all the time, except depending upon the object you're working on, there may be additional stuff present. Like for the chart, for the pH, the water analysis, we have to tell you what changes we made to the system in order to, let's say, match charge balance or alkalinity or pH or whatever it is. Okay, now that that's done, we're going to use these two waters in a next calculation object where we're going to mix them together and see what happens. But to do that, really what we have to do first is rename them, because you won't know what reconcile is versus reconcile 1. So let's call the first reconcile high calcium barium reconcile. Okay, and call this the second one high carb sulfate reconcile. The reason I want to do that is because I want you to get into the habit of labeling things. When you start building complex files where there's a lot of entries, right, you'll start losing your bearings on what things are. And so it's just better to get things labeled so that if you want to do a further calculation with it, it shows it's clear where it came from. And you're going to see that. I'm going to show that in 2 ways. First of all, let's say that you wanted to convert one of these reconciled waters to a stream, right? If I wanted to do a survey calculation on this water, this reconciled water, I have to turn it into a stream. So the way that you turn, again, chapter 2 and 3 that we did yesterday and Tuesday and today is all about taking a stream and operating on it. This reconcile object is not a stream. It's a calculation, and we have to convert it to a stream in order to do what we did prior. So at this level, at this object, you're going to see buttons over here down at the bottom. There's an advanced button, there's a search, there's an add as stream, and there's an export. I want you to use the add as stream button. Click on that, and then press OK. What you've done is you've converted that reconciliation study into a new stream. Okay? You can see now that the stream is now using molecular flows rather than cations and anions. It still uses concentration units because that's what the units were of your reconciles test. But now what you can do with this stream is do any calculation you want. Single point, survey, chemical diagram, corrosion rate, stability, etc. Okay, so now you have full access to all OLI calculations once you've converted this from a water analysis to a stream. And again, the way that happens is you use the add a stream button down here, or you can right mouse click on the reconciliation object and select add as stream. And again, one of the reasons why we want you to name things is because once you've converted it from a water analysis to something else, somehow you have to identify, where it came from. Now here it's easy because it says molecular export from this. And it also says the same thing in the description. Stream exported from. So as long as you've labeled this, you can identify where the source of this was, in case for whatever reason you rename it here. Okay. So there needs to be some sort of tie back, and that's why labeling things is good with this software. Okay. I'm going to delete this since we don't need it. You can do the same. Right mouse click on the, not the reconcile. Right, if you created that stream, we don't need it, so just right mouse click on it and just press the delete key. All right, select delete.